Come on. Yeah, there we go.
There you go.
I'm Jim Tannenbaum. That's my fancy picture from long ago. I am a senior principal engineer at United Healthcare, and I support the Optum STEM program. It's an outreach program out to high school and middle school students. I mentor those students in both internet safety. We start with Scratch for some of the younger students. We use Python for the older students. We'll use BIPES, which is what I'll talk about today, and MicroPython. And we also have created a small, relatively cheap bot that we use, or robot that we use to teach the kids collision avoidance. We use line following. It's based on a 3-wheeled chassis, very small and very cheap. So the kids love it. And, you know, if those of you who are using Lego Mindstorms, which my local school district was able to use, they have that kind of budget. But for us, with a very low cost budget, we can bring robots into the schools that don't normally have access to that type of thing. Today, we'll talk a little bit about the list of components that I'll demonstrate. We'll talk about a prototyping board. If you haven't seen a prototyping board before, that's what this whiteboard is that you see in the image. We'll talk about the Raspberry Pi microcontroller for those who are using microbit. It's same idea. We'll talk about what BIPES is, which is pretty much the main part of my talk, and then I'll do a demonstration of using BIPES, and we'll talk about different computational concepts. We'll use variables, we'll use loops, we'll use conditionals, functions, lists, and then we'll show the Pico being connected to all different types of components. You'll see some of them on the board now, and we'll get into each one as we go. So let's talk about the list of parts that we're going to see today. The half-size breadboard, which you see again in that image, the Raspberry Pi microcontroller, where you can't really see this black cable that goes to my computer, but the USB micro cable. A couple of resistors that we need to make sure that we don't overdrive these LEDs and have them blow up on us. A small button. We'll use a potentiometer, which is just a variable resistor. A photo resistor, so we can actually build a nightlight, which is kind of cool. See the kids do that. A NeoPixel display, which is this board up here. What it does is it contains basically 3 different colored LEDs. And so we can play with the colors that it generates and kind of walk along with that. We have a small digital display. We'll play with the joystick, a buzzer, which unfortunately you won't be able to hear because I'm using headphones. And quite frankly, being an older person, I don't hear it too well either. But the kids can hear it and they can play all kinds of different tunes, which they enjoy doing. And of course, a bunch of jumper wires, which you see floating across here. So the total cost for a kit like this, again, which we can bring into the schools, $20 to $25. Of course, if you start buying the pieces in bulk, it brings the price down. But again, these types of kits are very useful when you're actually talking to a student about Python. Thank you, Dan. I was going to post that, but you got there before I did. When we start talking to students about computer science and computer programming, certainly we can demonstrate loops and show them with a printout that it's counting from 1 to 10. But when you start getting the physical devices involved, it makes it much more real to them. So we can show them that, oh, this is what a computer program can do when it interfaces to the outside world. We can turn on lights, we can drive different types of displays, we can read inputs. And so we'll walk through some of the labs as we go through today, show that how that's working. So let's talk a little bit about our breadboard here. So our breadboard basically has a channel down the center, which separates the left side from the right side. We're using small breadboards in our labs. They're just, first of all, they're cheap. Second of all, we typically don't really stuff that many components onto the board. What you're seeing in my demonstration here is actually a combination of 3 different labs, or 4 different labs. That's not normally the way that we would do this. We would do 1 lab at a time, and you'll see that as we go through the lab section. The way this breadboard works is we have rails along the side. You'll see the blue lines and the red lines, typically what we use on the blue lines, and they're connected all up and down this rail or along this line. The plus gets the voltage side, the positive voltage, and then the negative or the ground goes along the blue side. If we look across A through E, or F through J, A through E are all connected. And so when we start asking students to stick components into the board, we'll tell them that kind of like Battleship, we say A1 is where you put one of the jumpers in, and then the other end of the jumper would maybe go up into A20. So we'll be able to easily talk through, show a student where it gets a little tough to see it in a small video like this. We can actually tell them, okay, this is the location for a jumper, this is the location for a component. We'll put the Pico itself starting in C1 and H1 so that it fits nice up towards the top. So you can see the numbers along the board, 1 through 20, which correspond to the pins. And then, of course, 21 through 40 on the other side. Unfortunately, breadboards are typically labeled 1 through 20 and 1 through 20. So sometimes you kind of have to do a little bit of math to figure out when you're talking about pin 40, is that it's on the J1 side as opposed to the A1 side. Any questions as I'm going along? Okay, Dan put more in the comments. Any questions? What ages and grade level is the curriculum? So for this particular curriculum, it really depends. I will typically use this in the elementary school or the middle school. If you use Scratch, you'll see BIPES is very similar to Scratch. Typically what will happen is I'll start a student, I might actually start with Python in either the middle school or the high school. And if they have problems grasping those concepts or understanding the syntax, I'll switch over to using BIPES or Scratch certainly for Python, and then BIPES for the MicroPython. Just because we want to sometimes hide that complexity, if you will, of the language or the syntax of the language, so they don't get caught up and stuck on that. Any other questions? No? All right, let me continue then. So the Raspberry Pi Pico, it has several inputs and outputs. So we'll talk a little bit about that. We'll demonstrate a bunch of them. All of these green pins that you see here are general purpose inputs and outputs. So they'll either be at a voltage 0 level or a voltage 3.3 volts. The red pins here, if you connect your computer on your USB connector, the V-bus will drive out 5 volts, and there's a voltage regulator on there, so we'll get that 3.3 volts out. Obviously, the ground pins are set up. If we look at these pink pins here, they are SPIO pins, and SPI stands for a serial peripheral interface. It's a way to talk to different components. You'll see that they're actually replicated, so we have the 0 port, and there's also the 1 port. We also have the I2 or the I2C component. That's the integrated circuit, very complex, but again, it's another way to talk to the outside world. And we also have 2 channels for that. So if you look, you'll see channel 1 and channel 2. Also, we have UARTs, very useful for talking to serial devices like a GPS if we wanted to get positioning information, or any other type of serial communication that allows us to talk via, you'll talk about baud rate when you talk about UARTs, and so we can talk to serial devices. On the other side, we also have analog to digital converters, which we'll demonstrate as well as we kind of walk through that. So the Raspberry Pi Pico, it was designed by the folks in the Raspberry Pi. This was their first microcontroller that they produced. It was designed in the United Kingdom in about 2020. It runs relatively quickly for a microprocessor at 133 megahertz. It does have onboard memory, so we could actually download an application to the processor and have it run by itself without being connected to the computer. We would do that by connecting in 5 volts or so into this VSys connection here with a battery, and then the computer or the microcontroller would run all by itself. It does run USB 1.1, so it's backwards compatible to just about any laptop, no matter how old. Or it has low power modes. It's got a drag and drop programming interface, which we're not going to use for the mass storage. We did talk about the different types of pins. There's also pulse width modulation channels. What pulse width modulation channel does, and we'll go into that, is a way to turn the digital I/O pins on and off very quickly. There's a temperature sensor built in. There's a timer built in. It does have floating point libraries built in, so it does floating point math very quickly. And we won't get into the state machines because that's really above and beyond where we want to be today. The chip itself ships as bare metal. By that, I mean that it has no programming or application language built into it. So we would go out to micropython.org and download the MicroPython interpreter. You'll see there's various versions of firmware that's available, but we're going to use the latest build. There are nightly builds, but they are considered unstable, experimental. So what you want is a full release, and you might as well get the latest release. So if you were going to install that, we have a little demonstration here. You go out to MicroPython, you hold down the boot button, and then connect up the computer. And then what you'll see on your computer is the MicroPython as a drive, and you can drag that UF2 file right onto the Pico, at which point the Pico will reboot. It'll no longer be visible to your computer, but you're ready to go. Questions about that? Nope. Okay, I'll keep rolling. So let's talk a little bit about BIPES. BIPES is a block-based, as I said, programming language or for embedded systems. It'll run on various microcontrollers. Does not run on the microbit, but it could. It could be extended to that. It was created by a team led by Rafael Roca, who's a professor at the Federal University of San Carlos in Brazil. Since it's open source, he allows many folks, including myself, to add to the application. And one of the things that I did, obviously, or maybe not so obviously, was expand the way that it works on the RP2040 processors. He was kind enough to allow me to load BIPES onto his server. So when we get to BIPES, you'll see that it has a Brazilian domain, which is fine. Anybody can use it. You don't have to install it on your laptop, either under Windows or under any other computer. It does run on Microsoft Edge. It'll run on Google Chrome. It'll run on Safari. So we're nothing to install. It runs just in your window browser. Why would we use BIPES? Well, we want to use BIPES because it hides the complexity of the programming language from the students. You can, in fact, see the programming language that we will generate using the blocks, but you don't have to look at that. And again, I'll walk through how you can go back and forth. If we just look at the BIPES application itself, there are really three pieces to think about. One is to select the serial port to connect to your board. One is to select the processor that we're going to use, and today is going to be the Raspberry Pi Pico. And then on the left side, you'll see navigation for various blocks that we can use in for the microcontrollers. Let me bring BIPES up real quick. We can talk through some of the other pieces. So when you first start BIPES, let me start it, load it. You'll see a screen come up just to welcome you to BIPES. There we go, splash screen. I'll talk a little bit about the boards that are available. Close that, we don't need to see that. We can select a series of boards and you can see a whole bunch of different boards that it supports. We're going to use the Raspberry Pi Pico, but it does use also the newest version of the Raspberry Pi Pico, which is the W, which means that it is web enabled. And it does use a couple of different 2040 based, RP2040 based boards. So they're all based along the RP2040 chip in the center here. We'll connect up serially to our board. And so we'll just connect. And you see that the connection shows that we're ready to go. So I'd like to spend some time walking through a set of labs that I've developed, showing different things that we can do with the Raspberry Pi Pico, and also introduce some of the concepts that we'll be talking about during the discussion today. So the first thing we want to do is talk about how loops work. We'll want to talk about how we can drive the different pins on the Pico. We'll talk about using a delay, and we'll talk about moving those blocks on the canvas. So let me go back to BIPES itself. And so the first thing that we want to talk about is just using the machine library and using an input-output pin. And we're just going to turn the embedded LED that's on the Pico on itself. So set up the pin. We don't have to do anything. There's no code here that we see. We hit show, run, and we've turned the LED on, and we can turn it back off, as so. And so, as I mentioned, you can actually see the code that gets generated from the blocks in the console. So if we wanted to talk about this, if we wanted to get into the code itself with the older students, we could talk about how we import the pin functions from the machine library. We could talk about the fact that it sets up a small function here to turn the pin on and off. And all we're doing is we're calling that function with the pin to either turn it on as we did above or turn it off here. But while that's kind of interesting in and of itself, what we really wanted to do was to turn the pins on and off, or turn the LED on and off. So we need to tell the students or explain to the students, we're going to grab a loop. And so what this loop represents is just a simple loop that we're going to run 10 times. Then we'll turn on one of our output pins, and we might as well turn on our red LED, which is sitting in our pin 21 or GPIO 16. And if we forget where the various pins are, we can always bring up the device map here, and we show, oops, we're plugged into the last connection here. So pin 21, which is GP16. So it's easy to go back and forth if we get confused on what we're turning on and what we're turning off. So if we just run this loop 10 times, we're not really going to see a lot happen. So let's make sure that we turn the pin off as well. And we can simply duplicate that block and turn it off. So if I was to run this, I would ask the students, does this work with iPads? No, unless, I'm sorry, I missed that question. Unless the iPad has a controller, which will allow you to go out serial. I've never tested it with an iPad. I don't see why it wouldn't work, but you would have to have some kind of adapter to allow you to get out to a serial port on an iPad. So Dan very nicely just mentioned that these Raspberry Pi Picos are available for $4 each. Thank you, Dan. I keep forgetting to mention things like that.
They are in stock in the Twin Cities too. So every Micro Centers have them, and there's been no shortages in the last couple of months. Unlike the Raspberry Pi themselves, which are 6 months backlogs. So the Picos are very available and low cost.
Very available. The one thing to consider though is when you buy that cheap $4 one, it doesn't have the headers soldered in. You can buy them with soldered headers. They're a little bit more expensive, maybe $5 or $5.25, depending on where you buy them from. So that's just one thing to consider when you go out to buy it. Or as I mentioned, in that kit price of $20 to $25, that includes the Picos that do have the headers already soldered in. Makes it a little bit easier. Thanks, Dan. But if we were just to run this application, you would see very quickly that we have a problem because it flashes the light very quick. I don't know whether you even caught it flashing, but its red LED will turn on very quickly and turn off. Well, that's not really what we wanted. What we want to explain to our students is that you really need some type of delay in between turning the light on and turning it off. And so now we've created a very simple application, turning the LED on and off. Right. And while this is kind of exciting in and of itself, let me stop the application from running and talk a little bit about why we'd add a variable to this. So we would add a variable, right? We want to create a variable, and we want to call that variable delay, for example. So very simply, we add a delay variable, and we'll give it a value, a numeric value. So that comes out of the math block. And let's set that to 0.5. And the reason that we want to do this is we want to show that rather than going into each individual section here in each individual block to set the delay, we can now use this one simple variable with our delay, which would just drag in like so. Let me duplicate that. And now if we want to modify that delay, we can have this light blink much faster, or we can make it even quicker than that. I'll stop and run it again. And now it'll blink quicker. and on we can go. And so what we'll challenge the students to do as we walk through this rather quickly, there's a challenge in how fast can you make that LED blink so that you can still see it changing. And so, that kind of gets a little bit of, hey, we can play with this. We can understand what's going on. We can understand how the variable works. We can try and figure out how quickly the eye sees that blink. Some of us will see that blink faster than others. As we age, we might not see it as quickly, but it makes for an interesting thing for the students to do, to kind of play with it and understand that that's why we added that variable, right? We could change that variable so that we can go faster and faster or slower and slower. And we only have to change it in one spot, which is really the point that we want to drive in the curriculum. How does that work? Why does it work? Once we move on from there, we can start dealing with putting 2 LEDs on the board. And once we have 2 LEDs, we can talk about how to make those LEDs blink in an alternating pattern. And part of what we'll have to do is, okay, very simply, right, we can duplicate blocks. So we can add another set of pins and make sure they go on and off. So let's go back to our BIPES setup. Come on. Go back to BIPES, and maybe we'll pull down. It's getting in the way. Let me see if I can put that over. There we go. Put that over here. So I go to BIPES, right? I can always add extra pins and say, sure, let's add another pin and let's turn that off. Make sure that turns off. Add another pin. Make sure it turns back on. Get the right guy. 17. And then when we're all done, we want to make sure we shut it all off. Drag down here. And okay, so that'll work for us, and we'll have it run a little quick, faster. And run. So now we'll go back and forth. And while that, again, is kind of entertaining for our students, what the challenge is we want to start adding more and more LEDs. And so it really doesn't become practical to add another LED, another block, another LED, another block. But if we only want one LED at a time, this construct rapidly falls apart. So now we start introducing lists where we create a list. We talk about how the list gets created, how we can add additional pieces onto the list, right? So we can click on this little gear here, and where the default block shows up, for example, list block, where the default block shows up as just 3 entries, we can actually click on that gear and start adding. If we had 4 LEDs or 5 LEDs, however many LEDs we wanted to add and use. So that's what the gear does for us. And then instead of having our pins set here, we can just create a pin and just put it in our list, which makes it very easy now. Let's go back to my alternating LEDs. All right, we create a list, and then we can walk through that list for each item in the pin. Additionally, we'll want to create a function. So we'll now start to talk about how to create functions using BIPES. And so functions work very similar to lists, where we have our function, we have our gear, we can start adding variables. And we may call our variable a pin, or we may have a pin list. And we probably want to name our function something other than do something. So let's call it set our pins. All right. So now I can have a function. I can call a function. Right? So I can go back to my function block and I can call that set pins with my pin list and the pin that I want to deal with. And I'll also need an if block. Right? So now I start getting into how logic works with an if block. So I'm inside my function, I want to walk through all of the pins in the pin list that I pass in. If the pin that I'm using is not the pin in my pin list, then I want to turn those pins off. So let's go back into my function. Call that pin something other than pin. We want to call that the set pin. And now inside that function, we would say we want to loop through all of our pins. So we'll get another loop. We'll loop through each. We can rename this to be a pin in our pin list. I'll grab my variable, pin list. And what do we want to do when we're doing that? Any pin that is in that pin list. So we need our if block. If our set pin. So I need some logic. Grab that over. I want to make sure that they're not equal. And if my pin, where's my variable? If my pin is not my set pin, then I want to turn that pin off. Move this out of the way. And I want to set that pin off. So we want to go get the variable, which is our pin, and turn it off.
This is the worst part. Nobody's getting paid.
I'm sorry? Is there a question?
Sounds like somebody went off mic. Could you? Thank you, Henry.
Okay. So the other thing that we want to do as we walk through this is we also want to turn the pin that we pass in, turn that one on. So we want to make sure that that happens as well. And so we'll use our variable set pin to turn our variable on. So we've now created our function. Move this over. Move this over that way. Created my function. We can repeat 10 times. Let's move this out of the way. Move this out of the way. And what do we want to do inside? Well, as I mentioned, we have our list. We need something called a pin list, right? So we created that function already, that variable already. So we'll set our pin list equal to our list of pins. We're only going to use 3 of these pins, so we'll move some of those out of the way. And we'll take our list of pins. Well, which pins do we have? We had pin 21. Yep, pin 21. And we'll copy that real quick so we can do that quickly. Okay, again. So we have 3 LEDs on our board. We'll use the 3 LEDs. So 17 and 18. So we've got that. We want to make sure that we walk through all of the pins in our list. So we'll need another loop for each item in our list. So we can just call this pin in our pin list. What do we want to do? We want to call our set pin. So we pass that in with our pin and our pin list. Oops. Oh, pin list. Again, we want a little bit of a delay, so we'll put that in there. And we lost setting the delay, so let's, oh, we did have the delay. So it should be good to go. And assuming that I built this quickly and correctly, we should see it set each one of the pins across. And again, that's a challenge for our students to kind of understand how all of these different pieces work. So we say, oops, one of our pins is left on. So we can also make sure that we turn all of them off when we're done. So we'll duplicate this block, pull it out, walk through all the pins in the pin list, and all we really want to do is just turn those pins off when we're finished. Make this run a little bit faster to make sure we didn't make any mistakes. And run very quickly. and they're all off. So now again, we've covered some concepts where we've hit logic, we've hit functions, and if we wanted to see how all of this really played out underneath, we can go back to our console. We'll see how we've defined that import from the machine library, how we've gotten time, how we've set up a couple of functions, and then actually walking through the code itself. Using a loop, using another loop for the list, turning on the pins calling that function, then delaying for a little bit, and then finally clearing out all of our pins. So we're now about half an hour into this talk. I'm going to go a little bit quicker. You won't see me quite running all of the applications, but we do have polling. So now we start talking about how we would use the inputs for the digital inputs rather than the outputs. So we'll add a switch, which we've added over here. We'll talk about what does that transition look like. If you've ever taken your light switch in your house and maybe slowly moved it up and down, you might hear a little bit of crackling. That's really this transitioning state here. When you press the button, it's never really a clean on and off. There's usually some noise that happens. So we have to be very careful as we're sensing what the switch is doing. How do we read that button? Well, we read a digital input from the pin that we have. We'll set the pull up to be false. So what we want in our pin here is that we want to tell the Pico that this pin is typically going to be at a ground or voltage 0 level. We want it to pull it down and make sure that it sits there. And then when we press that button, you'll see that we have our 3.3 volts along our rail to the button. When we press the button, it'll drive 3.3 volts into the input. And so what does this look like? We have a loop where we would read the input. We'd set that output pin to our LED state and the other output pin to not the LED state. So we blink back and forth as we press the button, and we wait half a second to make sure everything settles. So that this would be the basic premise of how that would work. Can we add more LEDs? Certainly. We could go back to our BIPES project, and in our blocks, we could continue to use this type of format, creating a list so that we go back and forth. We would need a variable block to hold the number of the pin. We'd have to have some logic there to change that variable. If you really want to see the code, it's down in the solutions, or see the series of blocks. You can see how the polling would work. Again, rather than showing you that dragging everything in BIPES, there's a solution for 2 or 3 or more LEDs, right? We would make that list bigger or smaller. Notice I talked about setting a pin number to pin number 0. Anytime the button is pressed, we would set the pin in the pin list, increment the pin number by 1. And then we would also want to use a little bit more math for those of us who have done algebra way back when. This is essentially the remainder function. So the pin divided by the number of pins in the pin list gives us a nice sequence from 0, 1, 2, and 3, or 0, 1, and 2, since there are 3 pins in the pin list. And when we delay, and every time we press that button, we would have the LED switch. So let me go back here, back to my labs. But there's a problem with polling. All right, one of the issues with polling, and let me go to the interrupt. Oh, another Pico has many LEDs. Yep.
Yeah, there's 26 LEDs on there, so you can do ports on there, so you can do a lot of different LEDs. But Jim is going to show you some more clever ways to do some of this stuff too.
Yep. So the other thing that happens, right? We won't change the board at all. But instead of using polling, which if you think about having you send a text message to a friend or an email to a friend or a co-teacher, when you poll, basically what you're doing is you're saying, hey, I've sent out a message and now I'm constantly looking at my phone, right? I bring my phone up, I look at it, I look at it, I look at it, I look at it. Instead, what we want to do is an interrupt. And what an interrupt does, again, think about your phone. You send out a message to your your friend or your co-teacher, and then you wait and your phone beeps and lets you know that you have a message. And that's much more efficient for the processor itself because it's not constantly going out there and trying to figure out what's going on. It essentially just goes to sleep, waiting for something to happen. And the interrupt handler, which again, we can use as we press the button and let go of it. So we set up an interrupt handler to say, okay, what I want to happen is anytime I press that button, wake the processor up, do something, and then let it go back to sleep. So to tie it all together, again, we have our LED state. We set up our interrupt handler. And so you'll see that pin that we have tied for the button. It's tied into, here I'm pointing with my finger, but I can point with the pointer. It's tied into that pin 20. And then again, inside our interrupt handler, all we do is we turn the LEDs on and off as we want, a little bit of logic to flip the logical state. But you'll notice in our while loop, all we're doing is we're sitting here and we're just doing nothing, right? We go to sleep for 10 seconds. We go to sleep for 100 seconds. We go to sleep forever. It doesn't matter, but we have to keep this loop going in order to keep the application running. Again, the challenge, adding more LEDs, using that pin list block, the set pins. So we'll basically do the same type of thing. Instead of polling, we'll rip out all of this and add the interrupt block. Again, those solutions are down here. I can start building it all out, but we are running short on time. So I'll just talk through the rest of the slides until we get to the joystick, because that becomes kind of fun for the students. So pulse width modulation, what is that? Pulse width modulation, stripping down the board to just a single LED and a single resistor. Pulse width modulation allows us to turn those LEDs or those outputs on and off very quickly. So what we have is two different things. We have the duty cycle, which is how often, or which is how long the output is on versus off. So we can have a 50% duty cycle. We can have a 75% duty cycle. We can have a 25% duty cycle. We can have a 100% duty cycle where it's on all the time. And then we have the frequency, which is how quickly these transitions happen from being on to being off. So how does that work? Well, we designate a pin to be a pulse width modulation pin. We set the frequency, how quickly we want it to turn on and off. And then we set our duty cycle. And our duty cycle runs from 0 to 65,536. So we can bounce back and forth for how quickly we want that duty cycle on and off. So much like before, what we'll do, and let me actually run this lab real quick. Take that out of here. And throw these over here real quick. Because pulse width modulation is a little bit different. We can start our pulse width modulation. We will use our external LED because it's a little bit brighter. We can set the frequency and we can set the duty to be 32,768. And actually, let's start at 0. And what we'll want to do is create a loop. So we can have our duty cycle. Try and spell duty cycle badly. There we go. We can have our duty cycle go from 0 to full on, which is 65,536. 35. We'll have it go a little bit quicker. We'll have it go by 10, go by 50. And what we want to do is set the duty cycle of our pin. So we'll set our duty cycle. We have to make sure that those numbers agree. So we'll make it 16. And we want to set the duty cycle to our variable. Duty cycle. And now what we should see is our bright red LED, assuming that I built this quickly, turn on and turn off. So I'll put a little bit of a delay in there. And wait a delay. Timing, delay. Like that. And now what we should see is that light slowly come on. So it actually looks like it's a dimmer, except it's getting brighter and brighter until it gets completely bright. And I'll stop that. And the other thing we can do is now duplicate and have it go the other way. 65, 535 to 0. And now have the counter count by -50. And so if we run really quickly, we'll see it get brighter. And then we should see it get dimmer. So the challenge here is what happens if we change the frequency? How quickly will we make it get brighter and dimmer? And again, we can use a list and change the frequency as we go along. But what you'll start to see is you'll actually see the LED flash as it turns on and off the duty cycle. So let's stop this. And I'll change the frequency to be something much smaller. And for anybody who is photosensitive to blinking lights, I apologize, but you will see the light blink significantly. So with a frequency of 100, you'll actually start to see it flicker as it turns on and off. Let's make that even slower. Change the frequency so that it's a little more obvious. Start to see it actually turn on and off. And so that duty cycle affects how long it's on and off, but the flickering happens because of how quickly we turn it on and off. And that's one of the things that we stress to the student. That is, what happens as you start decreasing that frequency? Can you actually start to see when it flickers? And what does that tell you about how you see things? The next lab, and I will bring out more parts so we can actually show you what those are. Disconnect. Take this set of parts away. Bring out a different set of parts. So the next thing that we do is we add a potentiometer or variable resistor. And so we show the students that not only can we read the analog to digital, which converts the voltage that we're sending to our variable resistor into a reading, which coincidentally is 0 to 65,536, or 65,535. So we can read that analog to digital converter and go back to BIPES. And rather than doing this, what we can do is create a loop that runs forever. We're always true. We can use our variable, or we can just use our, let's set our pulse width modulation. Throw that out. We'll keep that. And we want to read from our analog to digital converter. So we want to read our analog to digital converter instead of our duty cycle. And now we'll select our analog to digital converter pin, which is analog to digital converter 0 is the one that we're using. And now when we connect to our board, okay, stop that, start it again, connect to our board. There we go. Now I can use my potentiometer to set the brightness or the dimness, much like we use on our wall switches, where we can turn that brightness brighter and dimmer. So now we've just demonstrated yet another component, another way to read data from our Pico. Okay, we've got about 10 minutes left and I am very far behind, so I apologize if I'm going to go quickly. So the other thing we can do is use a photoresistor. And oops, I need to swap out again. I'm running out of board space. Another set of components that we can use is a photoresistor. And using the same type of process here from our analog to digital converter and reading from it, we can use it to create a nightlight. And so again, the board setup, building a nightlight with the photoresistor. Basically what the photoresistor does is if we think about the way that variable resistor does, the photoresistor, as I cover it, has a different resistance than when I leave my finger off of it. So I can read from the analog to digital converter and make a determination of when I want to turn this light on and when I want to turn the light off. So we will, again, be true. We will read our analog to digital converter. We'll throw a little bit of logic in there. If, and we need a comparison. So if I read my analog to digital converter, oops, let's try that again. I read my analog to digital converter. If it's greater than the value that I read from my analog to digital converter, let's say that we want it to be halfway. So 32,768. What do we want to do? Well, again, we need our little switch, our little configuration here. We want an else block in there. So if it's above 32,768, what do we want to do? We want to turn on the output. So set it to true for our pin 16 or our GPIO 16. And if it's below that, we want to turn it off. Right. So if you think about how a nightlight works, when it gets dark, we want to turn the light on. And when it gets bright, we want to turn that light off. So let's connect to our board. And run. Hopefully it's bright enough in this room so that when I cover it, we turn the light on, turn the light off. This is basically how a nightlight works, right? Same type of idea. There's just a little photo sensor in there. And when it gets dark out, the light comes on. When it gets bright out, the light goes off. And again, I keep talking about the physical computing here and the things, the logic that we're doing to make things work. It becomes interesting for the students because they can actually see what that logic does, what happens when you read an analog to digital converter, why that's kind of interesting and important. But again, it's more than just, it's more than just, oh, I have a program running, I have an if block, it's going to do something. I can't necessarily see, I'm counting from 1 to 10 versus, if it's positive or negative, I print something out. This shows how the physical aspects of that compute works. So the part that the students really like, with the couple of minutes that we have left, is this NeoPixel board. So the NeoPixel board has a built-in library. So you just initialize the NeoPixel board. And then all we need to do is control the NeoPixel board by setting that whichever pixel we want set to a particular color. So let me do that very quickly. We will create a loop. Just call it 0 through 7. We need to initialize our display. Our NeoPixel board is connected to pin 1. We have 8 LEDs we can count. And so with our NeoPixel strip, we'll just set the color. We'll use our variable K. And the thing that always gets our students confused is they forget to write the NeoPixel out. We are just a reminder, 2 minutes left in this section. Okay, thank you for that reminder. Quick delay here. We'll add a delay timing for 1 second. So what will happen is we'll end up setting these colors one at a time. And connect to the board. Let's restart that. Connect to the board. Connect. Run. And you'll see the LEDs go one at a time.
I have to just mention the kids just love these labs. This is really when they start to visualize how they can build costumes and all these other things. They can change the colors, the speed, the patterns. This is really when it starts to get fun.
Yep. So I know we're almost out of time. I'm going to skip quickly to the joystick. So we can actually add a joystick and a digital display. I hope I have a minute or two left, but I don't, but I'm going to do it anyway. Sorry for the people who want to jump to the next poster session, but let me do this very quickly. One of the fun things to do is to add a digital display and a joystick. The joystick looks kind of like a controller that you'll see on any of the game systems. I will quickly throw that away. Load the code since I, come on, load the code. Load the code since I built that previously. So apologies for why did it fail to parse the data. That's not good. Let's try that again. The joystick, because we're stuck here. There we go. All right. Well, I did have a cool lab to show you, but unfortunately, I think we're out of time and it doesn't want to load for me. Nope. Okay. Anyway, I apologize. Normally I would have showed you or run out of time. Are there any questions?
Just want to make sure everybody knows that this is really the basis for a lot of other projects. This is the robot that Jim and I have been building together. We have a $19 version and a $35 version that has a nice display on it. And this display has faces and it does all sorts of fun things. So this is really a gateway to really having a great time and getting your kids interactive with hands-on, although you got to work there, Jim.
Yep. Let me quickly demonstrate that. So I don't really want to walk through all the code. Well, I'd walk through all the code, but we're out of time. But eventually essentially what we're doing is we're writing to the display. You see it say, press the button to clear the display, press the button, and we can use the joystick to draw all kinds of lines on the display, kind of like an Etch-a-Sketch. So again, a lot of logic here. Initializing the display, clearing everything, running it, setting up that little message that we say, and then actually drawing lines on the display. A little bit of a calculation here to determine where we go. So there's some math thrown in there as well. So again, thank you very much for joining. I'm sorry that we went over, but I'm glad hope everybody got it. Please feel free to either grab the information that we put up and use it in your classrooms. Thank you.
And encourage everybody to connect with Jim on LinkedIn. He's a great mentor. He's taught us so much. I'll put his LinkedIn connection in the chat too. And so I'm looking forward to talking to anybody else that would like to do more hands-on coding labs. These are really fun.
Yeah, thanks, Dan. And
Thank
you
you
can catch
so
Dan
much,
later.
Jim.
Yeah, I'll be talking later about using ChatGPT to generate this code. So, all right, great. Thanks, everybody.
Okay, thanks, everyone.
Thank you, Jim.